Hi, welcome to me313 Mechanical Engineering and Thermodynamics. The topic of this video is the speed of sound, and the sections in the textbook are 17.1 to 17.2. So here are the three learning outcomes. At the end of this, you'll understand what we mean by compressible flow. You'll be able to calculate what are called stagnation properties, and they have the symbol T0, P0, and H0, for example. And you'll understand what the sonic velocity is and how to calculate it for an ideal gas. So first I want to talk about compressible flow. Just to give you a little bit of background here, there's entire books on compressible flow. So similar to like with the chemistry we saw in the previous chapter, we're just going to kind of put our toe in here and just look a little bit at compressible flow, but you can take the entire classes in compressible flow. But I wanted to say what we mean when we say something's compressible, because we've been dealing with ideal gases all semester, and those compress and they flow, and so what do we mean by that? And so let's just kind of start off by just kind of looking at an example here. And so imagine that we have a duct, and we have air flowing through this duct, and I have some inlet conditions. It's coming in with a mass flow rate of 1 kilogram per second, coming in around 20 degrees Celsius and 125 kPa. Goes through this duct with a cross-sectional area of 100 square centimeters, and then it comes out at a lower pressure, so there's a pressure drop through this duct, and this duct is also being heated at a rate of 10 kilowatts. And so the thing we want to answer is what's the outlet velocity and what's the outlet temperature. So we can go ahead and determine the outlet velocity from a mass balance, and so we know that the mass balance, or the mass flow rate is going to be equal to the volume flow rate over the specific volume, and if it's an ideal gas, we can replace the specific volume with RT over P from the ideal gas law. And then the volume flow rate is going to be the area times the velocity. So I'll do the velocity with a little arrow over it so that we know that it's not volume but the velocity. And so we can go ahead and solve this. And so let me just put some numbers in there. There's my 1 kilogram per second for the mass flow rate. R is 0.287. The temperature we have is 20 degrees C. We need to go ahead and put that in absolute because we're using the ideal gas law. So 293 over the pressure, which is 125 kPa. And then we've got the cross-sectional area, which would be 0.01 meters squared, if I convert my 100 square centimeters. And there's my velocity. And so go ahead and solve that for what the inlet velocity is. And the inlet velocity is going to be 84 meters per second. So right there, we've got our inlet velocity is 84 meters per second. We can go ahead and determine what our outlet temperature is, so then we can go ahead and get the outlet velocity. So we can go ahead and do an energy balance. We have, well, the energy going in equals the energy going out. So we have the mass flow rate times the enthalpy going in. And then we need to add Q to that, which goes in, and that's going to be the mass flow rate times the enthalpy that goes out. In ideal gas, we can replace the enthalpy with Cp. We have m dot Cp T1 plus Q equals m dot Cp T2. And if we just go ahead and plug in our numbers there, it's pretty straightforward to find out the outlet temperature is 30 degrees Celsius. So we have a 10-degree temperature rise, going from 20 to 30 degrees Celsius. And now that we know the outlet temperature, I can go back in and use my mass balance equation just now using T2 and find out what the outlet velocity is. And the outlet velocity is slightly higher. It's 87 meters per second. All right, so why did I go through that? Well, if you look closely at this energy balance, you'll notice that I neglected the kinetic energy terms. There's no kinetic energy terms in there. Why did I neglect those? Well, if we look at what those are, we would have 1/2 the mass flow rate times delta V squared, and that's going to be in terms of the kinetic energy. We find that that's very, very small, and it would only be about a 1% change in my outlet temperature. So it's fine to go ahead and neglect it when I've got small changes in velocity there. But what if we were to go ahead and change this problem, just go ahead and see now we're going to heat it up to 1 megawatt. So what this is going to cause is a much higher outlet temperature, and which means it's going to be much less dense and we'll have an outlet velocity. So if I was to go back through the same problem again, I'll just kind of skip to the steps are the same. We find out that the outlet temperature would be equal to 1020. That would be in degrees Celsius, so it would be very, very hot. And the outlet velocity, V2, because it's not very dense, would be 370 meters per second. Now remember, it came in at 84 meters per second. Now it's coming out at 370, and that's going pretty fast. And in fact, if now I was to look at what my change in kinetic energy terms are, with these kinetic energy terms here, I'd find out that that's going to be on the order of about 130 kilojoules per kilogram, right? And that's about Cp delta T. And so that means that about 130 of this degree changes is actually in the kinetic energy. So really my temperature should be like 1020 minus something on the order of about 130. So I'm now starting to introduce pretty significant differences. And so clearly I can't neglect my changes in kinetic energy when my velocities go fast. And the reason this is called compressible flow, when we need to make sure we always include kinetic energy terms, is because what causes this large change in kinetic energy is the fact that the air is compressible. Here it is, it's not being compressed, but being decompressed. But because it's having such a large change in density, because of the compressibility of it, getting large changes in velocity, we need to account for these kinetic energy terms. And in fact, we've done this before. It was just instead of looking at ducts, we called them nozzles. And once we had a nozzle, we said, oh, well, we obviously need to include kinetic energy because that was the point of a nozzle. So here what I'm saying is even if you don't have something of the classic nozzle, you can have just simply a duct. If I have large changes in kinetic energy, I need to account for them. So in the end, the way to think of it is when things start going really fast, and we'll talk about what we mean by fast relative to what, we need to account for changes in kinetic energy in our energy balances. So that's what we're going to be doing in this chapter. And this is actually nothing new. As I said, we've done this all before when we dealt with nozzles, but we're just going to kind of introduce a little bit of new terminology that's used classically in the compressible flow literature. So first, before we go into the speed of sound, I want to talk about something called stagnation properties. And the concept here is pretty simple, and this diagram is pretty good of it. What this diagram is attempting to show from the textbook is that if I have something flowing, like air flowing here, and it was at a particular velocity, it was to come to a complete stop, the kinetic energy that it had is going to be then converted into internal energy, and its temperature is going to rise. And so that's what this diagram is showing. So when it comes down to a complete stop, it's got a rise in temperature. So when we talk about stagnation meaning stop, we're talking about properties that are out here when it's moving that it would have if it came to a complete stop. Right? So let's go ahead and look at how we could determine what those are. Let's do an energy balance for this material. So H1, which is the internal energy, plus the kinetic energy term, because we determined that we can't neglect that. So this is going to be 0.1 out here where it's flowing, and that's going to be equal to H2 plus 1/2 V2 squared, and this will be 0.2 when it is completely stopped. And well, we just said that if it's completely stopped, the outlet velocity is 0, and if this is an ideal gas, and everything we'll be dealing with in this chapter, we'll be dealing with the ideal gases. So we'll have Cp T1 for my enthalpy plus 1/2 V1 squared, right there, and that right there is going to be equal to H2, which is just Cp times T2, and there's no final velocity. And so this temperature T2 is what we're calling the stagnation temperature. It's the temperature that the air would have if it came to a complete stop. And so we're actually going to call that T sub 0. And I realize this is a little confusing. Back in Chapter 8, we talked about the environment being at T0. There's going to be some notational changes here in Chapter 17 you're going to need to be careful of. So we're going to use the sub-zero notation for things that are at stagnation. So again, this is the temperature the air would have if it came to a complete stop. All right. So now I know what T0 is. I'll just rearrange that. T0 is going to be the particular temperature, and then what I'm going to be doing is adding this term, which is going to be V squared over 2 Cp. So it's sort of like I'm adding this kinetic energy term. So one thing to realize, stagnation will always be greater than the temperature, and it's going to be proportional. That increase is always going to be kind of proportional to what my velocity is at that point. Okay. So this is the stagnation temperature, and now we can talk about things like stagnation pressure and stagnation specific volume and stagnation enthalpy by simply what are all those properties at point 2 when it came to a complete stop. So we're going to do another assumption. We're going to assume that when it came to a complete stop, it did it isentropically. So there was no change in entropy. And if that was true, we can use these relations to remember from Chapter 7. For example, T over T naught is equal to P over P naught to the K minus 1 over K. So this is just going from 2 points isentropically. And so now I'm just saying, okay, I'm going from a T and a P to a T naught and a P naught. And so there right there is an equation for what is called my stagnation pressure. I can do a similar thing with volume. So remember we had V over V naught is equal to T naught over t to the 1 over k minus 1. Again, just an isentropic relation. And so from there, I can talk about what my stagnation specific volume is. And now here, a little bit of danger again. Compressible flow literature, they don't tend to use specific volume. They tend to use density. And so remembering that the specific volume is just 1 over the density. The equations you'll be seeing in this chapter are actually going to be something like rho naught over rho, which is the density. Simply T naught over T to the 1 over K minus 1. So it's just the inverse of volume. Just classically what happened, we use density instead of specific volume. But you can always get one from the other by just taking the reciprocal. And the last stagnation property I'll talk about is the enthalpy. So the stagnation enthalpy, it's the enthalpy it would have if it came to a complete stop. So that's going to be the actual enthalpy it has, plus I'm just going to go ahead and add the velocity that it has. Oops, not substitute. What I meant to do is square that. So it's just going to be 1/2 v squared. So I'm just going to be adding the kinetic energy term, and there's my stagnation enthalpy. So now we've just defined stagnation properties: temperatures, pressures, densities, and enthalpies. Okay, so we're going to come back and use those, but first now what I want to do is go ahead and derive an equation for the speed of sound, or what's also called the sonic velocity. So those are meaning the same thing. And so here's kind of the thought problem. This is just going to follow through what's going through in the textbook. So here's the idea. I have this sort of a piston inside a duct that's maybe full of air, and I'm just going to go ahead and maybe hit it with a hammer, causing it to move to the right with some velocity. And that velocity we're going to call dV. And what that's going to do is it's going to cause this compression wave to move through. So you imagine that I've got some gas molecules over here. If I go ahead and push this forward, I'm going to go ahead and compress this a little bit on the right-hand side, and it's going to be slightly higher density on the left-hand side than the right because I went ahead and compressed it. And now what we're going to do is we're going to do an energy balance over this wave. And this wave is moving with a velocity. We'll call that velocity it's moving c. We're going to find out that's the sonic velocity. That's the wave, the speed at which this wave is moving, where I have less dense material on one side and high density material on the left-hand side. And you can think if you were in a really crowded room and somebody was to push somebody else out, and there's sort of like a wave as everyone knocks the person in front of them. That's precisely what's going on here. These molecules are knocking these other molecules over on the right-hand side. So that's what we're going to go ahead and work with. And so we're going to do a couple balances. And so we're going to start off with a mass balance. Again, this is my control volume. And the control volume is moving to the right with the velocity c. Okay, so kind of keep that in mind. We're moving to the right. And so clearly, if we're not collecting material at this boundary here, the rate that energy is coming in from the right, so this is going in the opposite direction of the velocity, the rate the material is entering from the right-hand side has to be the rate that material is leaving from the left-hand side. So that's what we've written right with this equation here. And so we're going to go ahead and what's our mass flow rate? Well, on the right-hand side, we've got properties, for example, density out here. It's got a cross-sectional area, and then since this wave is moving with the velocity c, these molecules more or less are just standing there, and then they're getting hit by this wave that's moving at c. So from the reference frame of this moving wave, they're coming in with a velocity c. Now, what rate are they leaving? Well, it's more dense over here, remember, because it's gotten compressed. We have a slightly higher density, the same cross-sectional area, and now they're all moving this c, and I've got to subtract the velocity, this dv term, the rate this is pushing forward, because all these guys got pushed, so they're kind of moving to the right. Okay, now this interface is moving much faster than that velocity that I hit it with, and so they're just not going quite as fast to the left as it looks like from the right-hand side. So then I'm going to go ahead and subtract out that term there. So now I need to go ahead and multiply this through, and so you realize I've got a rho AC, I've got a rho times an A times a C, so those terms right there are going to cancel with that term right there. And then I've also got a d rho times a velocity term, and that term right there is about 0. And the reason for that is that v is much, much less than the speed of sound, the rate at which this piston moves. And so if I go ahead and put that in there, then with that assumption, I have 0 is equal to c d rho minus rho times v, all right? And so this right there, that's my mass balance. Okay, so we've done a mass balance. And so the next thing we're going to do is we'll do an energy balance over this control volume as well. And so it's going to look really similar, right? So what rate does energy enter? Well, it enters with an enthalpy C, and then there's my kinetic energy term, and it's coming in with the velocity of C, right? So, and then which it's leaving, well, it's going to have an increase in enthalpy, or at least a difference in enthalpy. And then I've got my kinetic energy term here as well, and again, I'm going to be subtracting V from the velocity C. And so if I take the C minus V term and go ahead and square it, you'd have C squared minus 2CV plus V squared. And again, since the velocity is much less than the speed of sound, this term right here, once I square it, tends to be pretty small. So I can go ahead and neglect that term. And so again, I can cancel this H with that H there, and then I've got a C squared that's going to cancel with that term. So I'm going to end up with just simply that DH is equal, or sorry, DH minus C times V is equal to 0. And that's going to be my energy balance. So just to kind of review, here's a mass balance over this little control volume. It's moving at the speed of sound, and here's an energy balance over it as well. So we're going to keep developing this equation. We're going to do one more thing. So again, here's my little diagram. If you think of this moving wave, what this is effectively is you can think of it as a pump or a compressor, taking something with low density, putting that in, and something with a high density coming out, right? So my wave is effectively a compressor with my inlet conditions over here on the left-hand side, my outlet conditions on the right where it's going to be more dense and it's got some amount of work that goes in. And so now if we'll assume that it's isentropic, which means that we're going to go ahead and do this compression isentropically, no change in entropy at all. The minimum amount of work for my compressor, if you might remember this from chapter 7, is going to be VdP. So the differential amount of work is VdP. And again, because of compressible flow notation, we tend to use density instead of volume. So I have dP over rho. And that's going to be equal to dH, because if this is isentropic, it means it's reversible. And Q is equal to 0, so there's no heat transfer. So this right over here is an isentropic relation. Okay, so let's review what equations we have. The top one over here, this was a mass balance. The second one down here, this was an energy balance. And the third one right over here is an isentropic relation. So I've conserved mass, conserved energy, and I've done my compression isentropically. Okay, so now we can go ahead and solve essentially, we'll combine those three equations right there. And if we do that, we get an equation that says C squared is equal to dP d rho at constant entropy. Okay, so let's look at what this is. This is saying what's the change in pressure with density, and when I go ahead and do it isentropically, an isentropic compression. And so we can go ahead and determine what this dP d rho term is. We did that chapter 7, right? We have P over P naught is equal to, again, we're going to stick with density. We'd have rho over rho naught to the K power. And from that, I can go ahead and determine what dP d rho is. dP d rho for an isentropic compression is going to end up being equal to K P over rho. There's a little bit of substitutions that go in there, but that's going to be the equation I can put into this value for C. And then one last thing I'm going to do is I'm going to assume it's an ideal gas. And because it's an ideal gas, I can use the relation that P is equal to rho RT. That's the ideal gas law. And so now I'm going to combine those three equations, this isentropic relation with my ideal gas, and I have an equation for what C is. And C comes to be the square root of KRT. K is the ratio of my heat capacities. And so this right here is the speed of sound of an ideal gas. So we've done energy balance, mass balance. This compression is occurring isentropically. It's an ideal gas. There's an equation for what my speed of sound is. And just another thing in terms of notation, we often talk about the Mach number. And the Mach number is just what's the actual velocity normalized by the speed of sound. So Mach 1 means we're going at exactly the speed of sound. Mach 2, we're going twice the speed of sound. Mach 0.5, we're going at 1/2 the speed of sound. Okay, so with all that, we can now go and do an example here, where now I've got a nozzle, and this is a sonic nozzle, so I've got some inlet conditions right over here, and this is my outlet pressure. I've got a 500 kPa pressure drop through this nozzle. That's a huge pressure drop through a small little nozzle like this. And so what I want to do is I want to find out the outlet, what is the temperature. So I'm sorry, that's actually P2. want to find out what is T2, what is V2, and what is the cross-sectional area at the outlet. So I'm looking over here at the outlet. It goes going in that direction. I want to find those three conditions. And so I'm going to assume this is an isentropic nozzle, and we're going to assume it's going so fast and I need to include my kinetic energy terms. Okay. So with that, what I can do, and this is where it's pretty useful with these stagnation properties, we're going to go ahead and define or determine our stagnation temperature. And our stagnation temperature is the inlet temperature, plus we added this kinetic energy-like term, which is V squared over 2 Cp. Okay? And this velocity, 1 meter per second, if you stick that in there, you find out that's going to be pretty small. That term is effectively 0. This is effectively just equal to T1, which is 200 degrees Celsius. So my stagnation temperature is just my inlet temperature, which is 473 Kelvin. It's pretty useful to always change everything into Kelvin because you're using a lot of these isentropic relations where you're going to want everything in absolute temperature. So there's my stagnation temperature. All that says if I had air at 473 and I brought it to a complete stop, it would still be at 473. So it's pretty small. But what's nice now is I can go ahead and use these properties I had where I have T0 over T2, right? So that's my stagnation over my outlet is equal to P0 over P2 to the K minus 1 over K. I'm sorry, that's P0 over P2, and that is P2. So that right there is my outlet pressure. So I can now find my outlet pressure from my outlet temperature. And with this one equation, I can conserve mass, energy, and I did it isentropically. So there's going to go ahead and give me my outlet pressure. I can go ahead and find out what my outlet velocity is, because T0 is going to be equal to T2 plus V2 squared over 2 Cp. So again, I'm using this stagnation temperature to find my properties at any point. I'm finding them at the outlet, which is at point 2. And so this tells me what my outlet velocity is, V2. And then if I want to find the cross-sectional area, I can do that from a mass balance, where mass is going to end up being the P over R. And if I do this at the outlet, P2 over T2, velocity to area 2. And now I can go ahead and solve for what the outlet velocity is. Right? So if I look at these equations, again, I have an isentropic relation there. I have an energy balance there. And I've got a mass balance there. So those are the three relations that we're using each time. If I give you some numbers for this, you find out that T2 is equal to 421 Kelvin. So it's lower. It started at 473. Now it's going really fast, and so it lost energy, and now it's down to 421. The outlet velocity is equal to 322 meters per second, which is pretty fast. And the outlet velocity, A2, is equal to 3.7 square centimeters. So I got that from the math balance. So now I can go ahead and find properties. I can find properties here. I said at the exit. I can find them at any point through this nozzle. So keep in mind, it comes in at 1500, and then at some point it's going to be 1400 and 1300 and 1200. And at each point through that nozzle, I could just go ahead and use those three equations and determine what my conditions are through the nozzle. And what I'm doing is I'm conserving mass, conserving energy, and I'm doing that compression isentropically with constant entropy.